Let's try to evaluate the indefinite integral 1 over the square root of 1 minus x squared dx. And you might try something like u substitution, but you'll find out that it doesn't get you very far with this integral. And so instead, we will do something called trig substitution. And the whole idea behind trigonometric substitution is to substitute for x so that with a trig function, so that this might simplify using some trig identities, and maybe it'll turn this entire integral into something that we can actually integrate. And so the trig substitution that we'll do, and the big clue here is when we see this 1 minus x squared. In fact, if we ever see an a squared minus an x squared, so 1 is 1 squared minus x squared, it's a pretty good clue that we would want to substitute with something times sine of theta. In this case, if we just make the substitution, if we say that x is equal to, let me do it over here, x is equal to, if we say that x is equal to sine of theta, then what we have under the radical right over here is going to become 1 minus sine squared theta, which is cosine squared theta. And then we could take the square root of that, and that might simplify all of this business a good bit. And we just want to make sure that we're not artificially constraining our x more than what the domain here would otherwise constrain our x. So if you look over here, the x cannot be, the x right over here has to be has to have an absolute value less than 1. Or another way of saying it, the domain right over here, x has to be greater than negative 1 and less than positive 1. If it was 1, then the denominator right here is going to be 0. If it was greater than 1 or less than negative 1, then all of a sudden you're going to have a negative under the radical sign. So already our domain is constrained for these values of x. So if we say x is sine theta, this actually allows x to be anywhere between negative 1 and 1, including negative 1 and 1. So we're not constraining x more than the domain has already constrained it. Since we're going to have to unwind the substitution later on, let's also define theta in terms of x. So let's say, and in a way that's not consistent with this top statement. So let's also say that theta is equal to arc sine, or inverse sine, of x. And what does this do? Well, this actually constrains what our theta is going to be. If I draw a unit circle, my best to draw one. So this is my unit circle. And if I come up with a particular x, that's going to be essentially the potential sine value. Arc sine is going to give an angle that is in the first or fourth quadrant. So if we say that this is our sine, if this is our x, then the arc sine of x is going to be this angle, not this one out here in the second quadrant. If we say that this is our x, then our arc sine is going to be this angle. So this right over here constrains theta to be less than or equal to pi over 2. So less than or equal to that, and greater than or equal to negative pi over 2. This is the way the arc sine function is typically defined. It will return a value between negative pi over 2 and pi over 2. Or another way of saying that, in this range right over here on the unit circle. And this will be important later on when we try to simplify this expression. But let's actually try to simplify it now. Before we do that, so we could substitute x, but we're also going to have to substitute for dx. So let's figure out what dx is equal to. Dx is equal to, well, the derivative of sine theta with respect to theta is cosine theta d theta. So now we're ready to actually evaluate, or at least simplify. So our original integral becomes the integral of 1 times dx. Well, dx is cosine theta d theta. Cosine theta, I'll put the d theta out here, over the square root of 1 minus x squared, which is now going to be 1 minus sine squared theta. Well, what is 1 minus sine squared theta? Well, that's going to be cosine theta, or cosine squared theta. Let me write this down. 1 minus sine squared theta is equal to cosine squared theta. This comes straight out of the unit circle definition of trig functions. Cosine squared plus sine squared is equal to 1. So we can rewrite this as being equal to the indefinite integral of cosine theta d theta over the square root of cosine squared theta. Now we have to be a little bit careful here. We have to think about whether cosine theta is going to be either positive or negative, or maybe we don't know. If we square a number and then take its principal root, we're essentially taking the absolute value of it. If cosine of theta was, say, -1, and we square it and then take the principal root, it will get 1. If cosine theta was +1, then we still get 1. So right now, all we can do without knowing more information about cosine of theta is say that this can be rewritten as cosine theta over the absolute value of cosine theta. Over the absolute value of cosine theta. If you square something and then take the positive square root, the principal square root, you're essentially just taking its absolute value. And so it's really tempting to simplify this more, but we can't quite do it without understanding what cosine of theta is going to be equal to. Well, lucky for us, we've already constrained theta to be equal to arcsine of x. And so that says that theta is going to be between -pi/2 and pi/2. And in this range of thetas, we're always in kind of the positive x-axis. So cosine of theta, which is the x-coordinate for wherever we sit on the unit circle, is always going to be positive. And since cosine of theta, so let me make this clear, arcsine of theta is equal to arcsine of x tells us that cosine of theta is going to be greater than or equal to 0. It's going to be non-negative, I guess is the best way to say it, not necessarily positive. It could still be equal to 0. So it's going to be non-negative, and since it's non-negative, the absolute value of a non-negative number is just the number itself. So this is just going to be equal to the integral, and I'll just do it in one color, of cosine theta over cosine theta d theta, which is just equal to the integral of d theta, which is equal to theta plus c. And now all we have to do is unwind this substitution. We already know that theta is equal to arcsine of x. So we could say this is equal to arcsine x plus c. And we're done. Using trig substitution, we were able to evaluate this indefinite integral. And another way you could think about it is we've just figured out what the derivative of arcsine of x is. By taking the antiderivative of this, we got arcsine of x plus c. If we take the derivative of arcsine of x, we get this business right over here.